All right, welcome everybody to Multiple Linear Regression Part 2. So where we left off in Part 1, we were talking about residuals, and we were talking about how our modeling assumptions can be used to show certain properties of the residuals. And so we can invalidate or refute the modeling assumptions by looking at their structure in the residuals, and that's called diagnostics. So performing diagnostics on a linear model is looking at the residuals as a way to see which assumptions are invalidated and which assumptions are reasonable. And so where we left off was this question, this cliffhanger that I left us with in the previous lecture, part 1, which was how can we fix broken residuals? Okay, so this is what this lecture is going to be primarily about, part 2. So there's this is just going to be a long list, and we're going to break them down in detail in the remainder of this lecture. So the first thing we can do is transform the predictors and or the response. Okay, so this is basically, we have some relationship which we posit, which is y equals, beta. I don't know. Let me write it in the simple linear regression form because it's a little more clear. Let's say we have a simple linear regression model, and it could be that the true relationship between x and y is actually not linear in this way, but in fact it is quadratic. And so what it could be is that instead of being linear, it could be that y is equal to beta naught plus beta 1x squared, right? So as x increases, y increases with the square here, okay? And so if this is your true relationship, this, for example, looks similar to what we saw some time ago. I gave you this, right? This example, which was y related to x. We stuck a couple models through it to talk about some residuals. But this is y equals approximately negative x squared or something like this, right? We have a negative quadratic relationship. And so if this is true, what we can do is we can basically just take this predictor and say, okay, so this is our first predictor. I can just say, well, let's define a new predictor, which is x2. And x2 is defined, this little colon equals means I define it as the first predictor squared, right? It's different information, right? And then I'm going to say, so instead of using this first predictor, instead of using a model which is x beta 1x, which looks like this, I can have a model which looks like this. So I say beta 0 plus beta 1 x2, for example, where x2 is just a square, okay? This is just a little bit of magic, but the deal is that I can just treat a certain transformation as of a input variable, of a predictor, as a certain transformation as its own predictor, right? So what I have here is I'm defining a new variable x2, which is just squaring the first one, and then this relationship between x and y is linear in x2, right? Similarly, I could say, well, instead of predicting y, I could do something like predict the log of y. So instead of predicting y, I could say, well, maybe the true relationship is log, I don't know, log base 10, for example, of y is beta 0 plus beta 1 x1 squared, right? So this is sort of the true relationship that I was positing before, except for I'm taking the log of y. Okay, so this is, and so what I can do is I can say, well, take x2, again, x2 equals x1 squared. It's a transformation of the x1 variable, and I can just say, well, I'm just going to have another, I don't know, y prime, for example, which is log of y. And then I have y prime is beta 0 plus beta 1 x2. This is a linear relationship between a transformed y and a transformed x. Okay? And so this is a valid linear model, right? What we're doing is just finding a transformation which makes this model fit good. And this is this summarizes point 1, transforming the predictors and or the response. So the name of the game is going to be finding these transformations. Maybe we can manipulate y a little bit, maybe we can manipulate x a little bit, so that it's reasonable that y is some expression plus some noise term which has nice properties, where the properties are some of our modeling assumptions. Okay, in particular, so this is a subset of transforming predictors. We can add powers or polynomial transformations of predictors into the model. Okay, so this is something I was just talking about just a moment ago, which is that polynomial transformations are a specific kind of transformation, and R has some customized commands to facilitate polynomial transformations like squares and cubes and things like this. And so if you use this command, so you do like lm y this tilde poly x w, okay, w is some integer, you would build a polynomial predictor of degree w and all smaller powers. So I'll illustrate this with an example in R later, but what this means, so let's say you say y poly x3. What this does is this does y, this does x1, it does x plus x squared plus x cubed. Okay, and so sorry, I'm thinking all of this is in an LM function. Okay, and so poly just gives you this expansion. Okay, there is some subtlety here. I'll talk about this in a little bit. It doesn't exactly give you these coefficients. It gives you some transformation of these coefficients, but it lets you build a model of polynomial degree 3. Okay, and lastly, there's some specialized syntax here. So these symbols, this power symbol, and this multiply symbol and this colon symbol, they have special meaning in R formulas that aren't what you think they are. So in particular, if you just wrote, y as a function of x squared here, you would think you would just get x squared, but you don't, because there's the caret symbol means something in particular in R formulas, and so just we'll talk about what these are in a future lecture, what their special syntax means, but for now, if you want to include just a simple model which has x squared as a predictor, you have to wrap it in this I function, which means identity. And basically this just tells R, hey, you have this special syntax, don't use this special syntax, just treat it as exactly as I'm writing it. This is like an identity, don't do anything funny to it, just treat it as a squared input. So this is a special ways to do transformations in R. These interactions of variables, this is another thing. We're going to have a dedicated lecture on this, but actually these powers and multiplication and colon signs here, these are all related to what are called interactions of variables. And the idea is that you generate a new variable as the product between variables. Okay, and so if you use this multiplication sign, this multiplication sign, this colon operator, this generates a new variable as the product between variables. Multiplication, it is what's called a factor crossing. Okay, so this is what these special symbols in R do. So a factor crossing, what it does is if you take the factor crossing between two variables in R in an R formula, it generates the one variable plus another variable plus their product term. Okay, this is called an interaction term. Okay, so somewhat surprisingly, x1 factor cross with itself. Okay, what this gives you is just the original predictor. So this is what I mean about it does some counterintuitive things. This is useful for in some ways, and we'll talk about their applications. But this is another way to build new predictors from old predictors. You can use the colon sign. This just generates the product between two predictors. You can use the factor crossing, which generates both of them individually and then their product term. And then the caret symbol will generate factor crossings up to a given degree. Okay, so for example, if I square this sum here in an R formula, it will generate a factor crossing sort of expand it out. So what this will generate is an x1 term, an x2 term, an x3 term, and then their pairwise multiplications, right? And so you notice actually we have no polynomial. We have no terms of degree 2, right? And so this is what I mean about being careful. So we generate factor crossings are the goal with these symbols here, and these this colon operator generates the product. Okay, so these are a bunch of things you can do. There are some problems which you're not going to be able to transform predictors into responses in order to fix the residuals and reconcile those broken assumptions. And so it's okay to just throw up your hands sometimes and say, hey, we've been through a bunch of steps, we tried a bunch of things, we cannot get this good structure to hold in terms. And when I say good structure, I'm referring to modeling assumptions. And so try a bunch of things. Sometimes it's just not going to happen. So the poly function, I mentioned that the poly function doesn't generate coefficients for these polynomial. Doesn't generate polynomial coefficients by default. By default, it actually generates it generates an orthogonal basis of polynomials. And what that means is basically it generates these three polynomials such that they are uncorrelated with each other, but that you can still generate a cubic polynomial from them. Okay, these are better. I'm not gonna talk about it a lot here. We'll talk about it a little bit in a future lecture. But if you want these actual standard basis, so where each one of your coefficients corresponds to a power of x, you need to give it a poly function an additional argument, which is raw equals true, and that tells R to not use this orthogonal basis of polynomials. Important that this does not affect your prediction. It only affects your coefficients. Okay, so what happens is you're generating the same polynomial coefficient. Need a C in there somewhere. And so what's happening is you're generating the same relationship between y and x. You're assigning. You have different predictors to do so. Okay, and the predictors are uncorrelated with an orthogonal basis, whereas the standard basis they are not. Okay. All right, so let's go back to this example, which is now almost overworked. We will leave it behind soon, but it's served us well for these first lectures. And here is an example. This is again predicting the percentage of residents in different communities who voted for Donald Trump in 2016, using as a predictor the percentage of search traffic related to NASCAR. Right. So here we have search percentage on the x-axis, percentage of votes on the y-axis, and as we increase x, we had this positive trend. This is a linear model we've seen in a previous lecture. We saw this bit of broken residuals over here, right, where the first assumption doesn't seem to hold because we are systematically overestimating the y values here. So this is an example where the residuals are broken, and we might suggest transforming either y or x in order to see if we can fit a better model. So let's do that. Oh, sorry. Here's an intermediate slide. I'm getting ahead of myself. This is, again, looking at the residual structure. So this is the original model, the broken residuals, just honing in. So this is the truth minus the predicted. And we see, again, here's those broken residuals where we have some evidence of breaking the mean zero assumption. So here's another, this is a multiple linear regression model. This is y predicted from a polynomial function of degree 2 of the NASCAR predictor. So here we're able to generate some curvature, okay? And so we're doing a little better here, right? But I might say we're still overestimating these points. All right, we're doing a little better, but we're still overestimating these points. Okay, so again here what we're using is we have a predictor which two predictors, right? Because I haven't specified raw equals true, These are not the standard basis, so they're not x and x squared, but I can generate polynomial functions with this basis, and here it is, right? So I can hone in on the residuals. Again, I still see evidence that things are broken over here. I'm overestimating. So maybe improvement, but not a solution. Okay. Here, just for visualization, I've plotted a smoothing spline. So we'll talk about what a smoothing spline is in a few slides, but basically what it is, it's a way to keep track. It's a non-parametric way to put a curve through a bunch of points. Okay, so we've talked about what parametric and non-parametric is. So basically what this is doing is this is tracking approximately the center of the points as we increase x. Okay, and so the smoothing spline is just helping me to identify, oh yeah, this is below 0. The points are sort of systematically below 0 in this region, according to the smoothing spline. As the smoothing spline tracks through these points, it says it predicts a little bit above 0, a little bit below 0, a little bit below 0, and a little bit above 0. I'm not super concerned with these regions. Yeah, they might be a little problematic in terms of the assumptions, but right, they're a little above and a little below. This region does seem to be more pronounced, right? These points also potentially problematic. With the smoothing spline is just a visualization which can help my eyes, because when we have a lot of points, it can be difficult to assess the health of the assumptions. So let's look at another transformation. So here I'm using a third degree transformation. So it's a third degree polynomial as a predictor, and I am getting better at going through these points, right? Less my overestimation. I maybe am still overestimating, but doing much better, right? And the original model sort of went through up here. I have the curvature that I need to get these points. And on the residuals bear this out, right? So the residuals, I don't really see the systematic underestimation as much. It's not as obvious, right? There's some points which are underneath, but if you presented me these points and said, no, really, for this x equals 2, this is a sample from a distribution which is mean 0. All right, I might say, man, I'm not 100%. I'm not entirely sure, but I wouldn't fight you about it, right? I mean, it's maybe believable given these residuals, whereas some of the previous residuals we've seen for different models, it was not remotely believable. Another one, so this is y as a function of the square root of x, okay? And so remember the square root curve, just generally the square root curve looks like this, right? Sort of like, and so y is square root of x, I sort of have this structure here. So the reason that why I actually tried this is because I know that the square root of x has this sort of dip down in this region, and I'm trying to use it to my advantage. It doesn't dip quite enough to get where I want it to, but it's an attempt, right? So this is another transformation, tried it. A lot of this is going to end up being guess and check. And I think that some students, when they are trying to find good transformations, they feel disheartened because they feel like they should know it right away. I don't know it right away. A lot of times I'm guessing and checking. So don't be afraid to try some things and say, oops, that didn't work. I haven't corrected my residuals. Try some things and see how it works. Again, here's a residual plot. Not as good as we were looking for the cubic model. Here I have the y as a function of log of x. Again, remembering the log of x function looks like this, right? And this is an asymptote that goes down this way. And so again, why did I try this? I tried this because, again, I'm trying to get this sharper curvature in this region, right? I'm doing better than with the square root, also potentially not as good as with the cubic, but I'm improving, right? So this is something which is, the assumptions are more reasonable looking at these residuals than they were, for example, in the straight linear model that we were using, the simple linear model that we were using at first. Some more weird things. So here's a transformation, log of y as a function of log of x. Just trying different things. I guess here, yeah. So just trying to get creative. Again, doesn't seem to be working too well. Still have some problems here, but just trying some different things, assessing residuals. And so, which is the best? Well, for me, as I mentioned as we were talking through, I think that the cubic model had the best residual structure. Okay, so for me, it was the model where I would say, okay, I would be willing to accept that mean zero assumption. We can go back and look at it really quick and say, would we be willing to believe the constant variance assumption? Yeah, maybe. I don't see examples where it seems like sort of the variance of the points is dramatically increasing or decreasing, or even visibly increasing or decreasing. We'll introduce some specialized plots for assessing variance as we go on, but seems reasonable to me based on the plots. So the assessment of the residuals, I will say, it takes a little bit of training for the eye. It is subjective. Okay, do your best. You can use visualizations like putting a line through the residuals at y equals 0. You can put the smoothing spline on the screen. I'll give the R code for that in a little bit to help your eye assess. But just do your best, right? And sort of there's some boundary there where you're like, well, does it hold? Does it not hold? Is it reasonable? To inform these decisions, one thing that can be helpful is actually simulation, right? You say, well, it looks like this. It's reasonable that this was be mean 0. Maybe simulate some random variables which are mean 0, and say, do you see some structure that looks like what you're seeing, right? Do you never see it even though you've done 100 simulations, or do you see it sort of reasonably occurring? Simulation can help inform your intuition here. So in general, the name of the game, we are going to hunt for forbidden structure in the residuals, that is violating this mean 0 constant variance uncorrelated assumption, or this mean 0 constant variance with Gaussian errors such that the epsilons are independent. Those are these 3 tiered assumptions. We're hunting for forbidden structure, and it really is using a lot of intuition and saying, is it reasonable if this assumption held that I would see points that look like this. So I mentioned we're going to have specific plots to assess the constant variance assumption. We're going to get into that now. Here's a fact. The fact is that the sum of the residuals will always be 0. Okay? You can show this from the normal equations. I'm not going to show this here. That's a little bit of an aside, but just introduce it as a fact, and we're going to roll with it. But it is indeed a fact that the sum of the residuals will always be 0. And so it will follow from that the sample variance of the residuals can be measured by their square. Okay. Now, why is that? What's the sample variance? So let's say I have a sample variance of the residuals, right? So it's 1 over n minus 1 sum ei minus e bar squared. So this is the sample variance, right? Now, if the sum of the residuals is always 0, what does that mean about the sample mean of the residuals, right? If we sum them all up, we divide by n. If we sum them all up and divide by n, that sum is 0, then this is going to be 0, right? So the sample variance is 1 over n minus 1 summation of ei squared. That's because the sample mean is 0, right? So when I say the sample variance of the residuals can be measured by their square, this is why. Okay, and so we can actually plot the square of the residuals and see as a proxy for sample variance. We can plot the square of the residuals because of the knowledge that the sample mean is 0. Okay, so we can plot the square of the residuals against the fitted or predicted value. This should be and this is a way to assess constant variance. We're looking for a constant mean of the square of the residuals as an assessment of constant variance. Okay. Sometimes, if you have large residual values which are extreme, it can be hard to look at it at on that scale. You can plot the absolute values of the residuals as a proxy for this. Again, looking for roughly constant mean. You can plot the square root of the absolute value of the residuals, and this plot will often create the best visual just because the residuals are more clustered together, so it's easier to assess their constant mean as opposed to being sort of spread all over the screen when you square them. Okay, so these are specific plots for assessing constant variance. So let's go and look back at the residuals. So this is the residuals of the cubic model. This was my favorite model of the models we were introducing earlier. And here's the residuals again, so we can look at the constant variance assumption. Again, not super happy with this region here, but I'm willing to accept it. We worked hard to try and correct it. And so here's another residual plot. Here I've plotted the residuals against a predicted value. So this is plotted against y hat. Okay, this is another area where I'm looking for constant mean. All right, and also constant variance as I can assess it. And here's the plot of the squared residuals. So the squared residuals, as we discussed, they can be hard to assess the mean, right? So here's a plot of the squared residuals. This is plotted against y hat, which is a valid variable for us to plot against. But it's a little hard to assess constant mean because of how large some of these values are. So one thing we can do, we can stick a line through these points, which is the mean of the square residuals, right? So the idea is as we track through and y hat increases, we should see that the mean is approximately this red line all through. I put a smoothing spline on there as well, just to help my eye assess this. The smoothing spline seems to have some issues here. This really large jump at this point here, I'm not putting a lot of weight on it just because it looks like the smoothing spline missed the trend and is just honing in on a specific value. But it does help my eye sort of track what's going on with all these points. It seems sort of reasonable that the residuals would be constant variance, and what I mean by that is that these squared residuals would have a constant mean. Maybe the variance is smaller, increases, and gets small again, but there's so few points here and so few points here. It's hard for me to put a lot of stock in it. Here's a plot of the absolute residuals instead of the square residuals. Again, the idea is that we don't blow up the scale quite as much when we do this. This is easier to assess for my eye. I see that the constant mean assumption does seem a little more reasonable here, right? And this is just another visualization to assess the same thing in this plot. This plot is just hard because we have a bunch of points condensed down here, a few points stretched out up here. The absolute value of the residuals makes that a little easier to assess. Spotting the square root of the absolute value of the residuals is even easier. And here's that. So we can see from this one, I see, all right, I'm willing to believe the assumption that the variance is constant. That is, that the mean of these points, the root of the absolute value of the residuals, is constant as we change this y hat value. Okay, so these plots, squared residuals, absolute residuals, or root absolute residuals, are three different plots that we can use to assess constant variance, and we're looking for constant mean through those points. And usually this is going to be your preferred plot just because the scale is such that it's easier to assess by eye, but the other plots will work as well. Okay, so this slide is just this is mostly just a literature review slide. Statisticians have thought long and hard about fixing broken residuals. There's many ways to do it. One way to do it is to look at points that are extremely influential or outliers. These are not synonyms. They actually mean different things. We'll talk about that. So outliers is a univariate concept. If you have extremely large x values or extremely large y values, you can throw them out as a way to say, you know, these are not indicative of the trend I'm trying to predict. Influential points are points which have which have an imbalanced impact, which have sort of an overweighted impact on the fit of your model. We'll talk about this in detail before this lecture ends. But influential points are points which have a higher impact on the fit of your model than other points. And by throwing away just 2 or 3 points, it sometimes happens that you can fix your residuals, and so these might just be sort of outliers in a bivariate sense. That is, they're not extremely large in the x or extremely large in the y, but they're extremely influential in a relationship between x and y sense, and maybe we have reason to discard them for the sake of fixing broken residuals. Okay. There are transformations that you can perform. I have automagically here, and this is me being a little bit sarcastic, but this Cox transform is a way to automatically find an optimal transformation of y, the response variable that fixes your residuals in a certain sense. So I'm not going to go into the details of it. The problem with the Cox transformation is that it's hard to interpret. Basically what you do is you find a transformation of y, which looks like y to the 1 over alpha, and you find a value alpha, which is good. Problem is that it can be difficult to interpret such a transformation of y. You know, if I said alpha is 0.1 or something, and you're going to predict y to the 1 over 0.1, and then you find a good model for predicting that y, how do you then take that to somebody who cares about the results of your model and say, well, I can predict this y to the 1 over alpha value, and it works quite well, and they're going to say, well, what is that? Why did you do that? And so sometimes it's easier to interpret square root value or square values, but just 1 over alpha for arbitrary alpha is difficult to interpret. But it can be useful. I don't mean to undermine it as soon as I'm introducing it. It can be useful in the sense that if you have nowhere to start, your residuals are broken, you're willing to do any transformation to fix it for the sake of maybe you're doing prediction and not inference, this transformation can be useful. It is the opinion of the author of the Truth About Linear Regression textbook. This is, if you read in that text, he introduces Cox Transform, and he sort of is of the opinion, and I share this belief as well, that Cox Transforms are they're talked about a lot in the concept of linear regression, but actually the reason that they were so used is actually that these statisticians, Box and Cox, who came up with this transformation, were very, very, very famous, and so they were very well known. It's like sort of a rock star that's a little bit past his prime, but very famous, such that when they put out a hit, or when they put out a song, maybe it's not that great of a song, but because they're so famous, everybody listens to it anyways, right? So, anyways, enough about Cox. Another way that statisticians have developed to fix broken residuals is so-called broken stick regression. Okay, so what you can do, let's say you have a model, or you say you have some points that looks like, I don't know, looks like this. You have something that looks like, you have some points, and then you have some other points. Okay, and so what you can do is you can say, well, I see a trend here, but I can fit a good model in this region, and I can fit a good model in this region. And so you can fit what's called a broken stick regression, which is basically just where you break up X and fit one model for some X region and some model for some other X region, right? Well, why is it called broken stick regression? Gotta love this name. Well, instead of being a solid stick where it's just sort of this line would progress on, because you have these two models, these two linear models, looks like a broken stick. All right, so haha. Almost as good as the hat matrix, but not quite as good. Another thing you can do is you can combine broken stick regression and polynomial regression in a smoothing spline. We've talked informally about what a smoothing spline is, but what a smoothing spline does is it fits piecewise cubic polynomials. Okay, so that is, it takes your points, breaks them up into regions, fits cubic polynomials in between. It enforces a continuity and differentiability constraint. Okay, and how it selects the not points is beyond the scope of this class. But what a smoothing spline is a piecewise cubic polynomial function. Sort of combines the idea of broken stick with this piecewise estimation and this idea of polynomial regression, because on each of the pieces here, you're estimating a cubic polynomial. Okay. The smooth.spline function, we'll do this in R. You can pull up the help menu for some more details. I'll also demonstrate some R code before the end of the lecture. Okay, so one of the things we mentioned on the previous slide is this idea of removing influential points. So let's talk about that in a little more detail. So we have this interpretation of the hat matrix. So just recalling that the hat matrix has this interpretation as influence, right? We talked about hat matrix is an orthogonal projection. That is, it's symmetric and idempotent, but it also satisfies this condition where the partial derivative of our prediction in the ith component, in the ith index, with respect to the response variable's input in the jth index is this hij term. Okay, so we talked about this informally when we mentioned it, which is what this says and why this is important is that we might have some observations for which changing the y input a little bit dramatically changes our y prediction, our predictions, right? And intuitively, that's sort of bad, right? What this means is that our whole prediction, predicting all future points, depends crucially upon, for example, a single observation in the jth index, right? And that's it's a lot to be riding on a single observation, okay? And so we call this a measure of influence, and in particular, there's a specific. So the idea of influence is how much an input influences an output, right, or impacts an output. And so, in particular, we're going to define a measure of influence called the leverage. Okay, so the leverage of an observation. In English, it's a synonym for influence. It's the leverage, but in statistics, it is a particular mathematical definition. So the leverage of observation I is the ith term along the diagonal of the hat matrix, right? So it is a measure of influence. It is the partial derivative of the ith prediction with respect to the ith input because of it's on the diagonal. Okay. So in general, it's a fact, and you'll show this in one of your homeworks, but it's a fact that the trace, the sum of the diagonals of the hat matrix, is p plus 1. Okay, and that gives us a scale for what is large. Okay, so for example, what this means is that so the leverage. Let's say that let's break this down a little bit. The hat matrix is n by n in general. Okay, and so I want to break down this fact a little bit more. This idea, scale for what is large, because it's an interesting idea. So the fact here is that the sum of the diagonal terms of the hat matrix is p plus 1. Okay. So if they were all, let's say all of the diagonal terms were of equal size, right? If they were all of equal size, then we would have that HII, the diagonal terms, were p plus 1 over n, right? Because we would be summing up the same constant value n times, so we could find that constant value by dividing by n, right? So this is our idea of sort of what is normal, or normal, what is typical. Normal is a loaded word in statistics. So this is typical, right? What we'd expect is all of these leverage terms should be near this value, right? Maybe some will be a little bit above, some will be a little bit below, but this is, if they were constant, they would be this. If we find a leverage value which is 8 times this value, we would say, ooh, that's weird, because one of the values would have to be lower to compensate for that in this sum, right? And so this is sort of the center which we can measure our leverage values again is p plus 1 over n, where again p is the number of predictors, n is the number of observations. Okay, so this is sort of what I mean when I say this gives us a scale for what is large. This is our typical, if they were all constant, so for them to all sum up to be some value, if one is a little bit larger than this, one must be a little lower than this, and so this is our point of comparison. In general, the idea is that the leverage is large when removing or changing the observation will dramatically change our prediction. Okay, that is the jth observation will change our predictions a lot. We know this in that the size, the magnitude of the partial derivative is large. So an alternative to leverage, this is an alternative measure of influence, is called Cook's distance. Okay, so Cook's distance is defined as follows. So we let y hat with a subscript paren I here. This denotes the vector of predictions when the ith observation is removed. Okay, so this is of length n minus 1 instead of n, because we've removed the ith observation. So Cook's distance, di, I'm going to denote it di, for the observation I, okay, is defined as follows. So what it is we say oh, excuse me, I made a mistake here. Let me clarify. Moving a little bit fast. So this is not an n minus 1 length vector. This is an n length vector. So we are predicting on all n points, but only using n minus 1 inputs to build the model. Okay, so that is the ith term. We're predicting a point where we didn't actually use that xy pair to build the model. So this is actually length n vector. Okay. The reason this has to be this way is because of this subtraction. So let me talk through this next. So we have omitted one of the xy terms, the xy pairs, and we've built the model using the remaining n minus 1 terms. But then when we predict on all of the observations. So what happens here is to compute the Cook's distance, you say the original. This is using the ith observation without the ith observation, so on and so forth. This is again without, okay, and then this is the true minus the model with the full predictions, and so on and so forth. Okay, so what is this saying? Okay, well, if I put, for example, for context, this helps me interpret this. If I put a 1 over n in front of both of these, okay, what I have in the bottom is the mean squared error. This is y minus the truth. Okay, and here I have y minus the prediction when I've just omitted one of the observations. Okay, so we can think about this as maybe a ratio of the mean squared error. This is saying how much does what is the mean squared error between y and y hat? And this is what is the mean squared error between y hat and y hat wherever I moved one of the predictions, right? So if y hat changes a lot when we remove this prediction, then this numerator is going to be large relative to this denominator, okay? And Cook's distance is going to be large, and this is going to say basically y or this I observation has high influence, okay? So Cook's distance measures influence with a different expression where we actually remove observations, okay? And so the idea, again, as we were talking about, Cook's distance is large. When removing that observation, the ith observations dramatically affects our predictions. So let's look at, this is called a leverage plot of observations from the cubic model of the models we were looking at from before. So we have the cubic model. Here's the leverages. So here I have leverage on the x-axis plotted against residual value on the y-axis. Okay, so we sort of have all these residuals, right? And then whatever observation corresponds to this value, this is extremely high leverage. Okay, so this is saying that this observation has a lot of impact on our model. If we were to change this observation, it would affect our model a lot. Okay, so what I'm going to do here, just for the sake of looking into this a little further, I'm going to select all the points where the leverage is greater than 0.1. I can compare this 0.1 to what we discussed earlier, this p minus 1 over n, right? Or excuse me, p plus 1 over n. So I can compare this value to p plus 1 over n, but what I'm going to do here is just sort of select this 0.1 as a way that's like, you know, chopping off some of the points and saying, all right, I want to look at some of the high leverage points and see if there's any trends between them. 0.1 is just a reasonable way where I have 4 points to investigate. If I broke it off over here, I might have a couple hundred, I don't know. So 0.1 is just what I'm going to go with as an idea of what is high leverage. So there's actually 5, not 4. I guess 0.1 actually captures this point. So the 5 observations with leverage larger than 0.1 are the following. Okay, so a metropolitan area in West Virginia, Texas, New York, and Hawaii. Hawaii sort of makes sense that Hawaii would have some unique behavior. I've been told that there is actually a NASCAR racetrack in this region, so this one makes sense to me that it has some odd behavior. Basically, what I'm looking for is are there reasons why I should discard some of these points? I'm looking for, these points have a lot of impact on my model. Maybe that's just because they don't really hold to the trend in general that exists between the x and y variables, and it might be beneficial to my model if I can toss them. Okay, you should find some interpretation before you toss them. Can you proceed by leverage is high, I'm going to get rid of them? Yes, but in general, it's better to have an interpretation for why, just because you could be throwing away points which are meaningful. Just because they have high impact on your model, they could be high impact points, but really represent the relationship you want to capture, right? So I'm just double checking the leverage to see, is there anything anomalous here? Makes sense. Maybe Hawaii has some different structure in terms of sports watching and voting. The fact that there's a NASCAR track here makes it seem like there would be high NASCAR watching no matter what happens in terms of voting. These ones are harder for me to parse. I don't have any particular reasons to believe that this behavior is anomalous. The behavior in these regions would be anomalous with the relationship, but it's worth checking. Plotting the high leverage points, I'm plotting them in red. So this is the points where the leverage is greater than 0.1. They are the regions over here. I think this is the New York and Hawaii point, and this is the Texas, West Virginia, and what was this? Virginia, Tennessee, Virginia, I guess. All right. Okay, so that is influence. Next, we're going to talk about assessing normality. This is something we've put off for some time. This is the third assumption, right? The third assumption is this idea that our residuals should be Gaussian, certain mean, certain variance. So you can assess the normality of the residuals with a couple of different ways. The first one is a histogram. The second one is a kernel density estimation plot, which is essentially just a smoothed histogram. The last one, and the one which I think is most reliable, is a QQ plot. And in a QQ plot, what you do is you basically plot quantiles against each other in a parametric curve. So what you do is you pick a quantile, you plot the pth quantile from one distribution against the pth quantile from another distribution, and you just repeat through the quantiles. And what ends up happening is you can actually see how the quantiles compare, and if the relationship is linear, then it suggests that, in particular, plotting a sample quantile against a ideal normal quantile, you can compare and see if the distribution is linear. So in R, in particular, you're not going to have to generate these by hand, coming up with quantile points, but you can generate a QQ plot comparing against a normal distribution or a Gaussian distribution with the QQ norm function. Okay, and if you see linearity in your QQ plot, this is an indication that the distributions match. Okay. So here's the histogram of the residuals in that cubic model that we've been paying attention to. For me, it's reasonable that it could be Gaussian. Here's a kernel density estimation, which is sort of a smooth plot of the residuals. Again, it's reasonable to me that this could be Gaussian. And here's a QQ plot. Okay, so again, what's happening is I have the theoretical normal quantiles on the x-axis, the sample quantiles, the quantiles in the y-axis are on the y-axis, and as I'm progressing here, so each one of these points is, for example, this is like the 10% quantile, right, or the 10th percentile. So I say the 10th percentile, where is that in the normal distribution? Where is that in my data? And I proceed. So this is like 10, 11, 12. It doesn't have to count by whole numbers, but the idea is that as we increase the quantiles, we should see that the relationship between the sample quantiles and the theoretical Gaussian quantiles, the ideal quantiles, should be approximately linear. And it is approximately linear here, and so we say it's reasonable that the third assumption, that Gaussian error assumption, would hold. All right. So there's a lot of plots. And instead of having to generate them all by hand, if you actually just plot a linear model object in R, so plot whatever is your output to LM, you actually see a lot of these plots all at once. Okay, so you can plot the residuals against the fitted value. That's the plot object. The plotting a linear model will generate a plot against the fitted value. It will plot the square root absolute value of the residuals. Again, this is for assessing constant variance. It will make a leverage plot, okay, which we were just looking at, and the Cook's distance will be given as level curves in this leverage plot. And then it will also plot a QQ plot over the residuals against a normal distribution. Okay, so that's the QQ norm plot. It will generate by default for you. So you can just plot an LM and get all these for free and not have to generate them by hand. Okay, I will mention that term plot is sometimes useful. Term plot will plot the residuals against the predictors. And actually, it's not exactly that. What the term plot will do is it will plot the expected value against the predictors. So just read the help menu for term plot. But what it will generate automatically something which can be interpreted as a residual plot plotted against each of the predictors. So you don't have to do plot against predictor 1, plot against predictor 2. The only thing is that it adds the prediction in there. So for example, let me just jump back really quick to an example here where I can. Okay, so for example, the term plot would plot the residuals and put this curve on there and plot it like this, right? So usually when we plot the residuals, we look at something like this, where we've subtracted off the expected value. Term plot will plot the predictor, that the part of the predictor that contributes to the expected value, and so then adds the residual onto that. So to assess mean zero, you just have to sort of reframe and center around this line that goes through it. All right, catching back up. Okay, and so then also many of these plots have a smoothing spline enabled by default. The idea is that that can help with your visualization. All right, just to track the mean, sometimes it can be difficult for your eye. Okay, so here I'm plotting what R generates by default. So you can see the command that I've done. I've generated a linear model using this third degree polynomial, and I plotted this object. So what R generates for me is this residual plot. So this is just the true residuals plotted against the fitted values, the y-hats. Okay, and here I have a smoothing spline plotted in red, the y equals 0 line plotted in the dashed line back there. So I can see, for me, it's reasonable that this would be mean 0 as y hat is changing. All right. Here is the QQ plot. We're plotting the theoretical quantiles against the standardized residuals. Here we can see, basically, as we're tracking through here, that the quantiles are increasing at the same rate, right? And so this is this curve is not invalidating the third assumption, so it seems reasonable that it could hold. Here's the square root of the absolute value of the residuals. Okay, so this one we're assessing constant mean, and if we see constant mean, this is an indication that we have constant variance in our residuals. We can also look at this plot and assess constant variance directly, but sometimes constant variance can be hard to assess, and so we have two different plots for that. And then here's the leverage plot. So here we have the leverage on the x-axis and the residuals on the y-axis, and here we have the Cook's distance plotted, the level curves for the Cook's distance plotted in dashed here. So what we can see is this leverage for this point isn't high, right? It's near, I don't know, 0.8, something like this. And not only is it high in terms of leverage, but it's high in terms of Cook's distance too. All of these points have Cook's distance less than 0.5, because 0.5 is the level curve here, whereas this point has Cook's distance bigger than 1. Okay? So that's how we can interpret them, and they come for free for us like this. And by sorry, these plots come for free, as in we don't have to generate them manually. Just plotting this LM object in R will give us all this information very quickly. Okay, so let's conclude with a little bit of R tutorial. So I'm going to switch over to my RStudio window, and we've seen this this code before. This is where we left off was we were looking at multiple linear regression models in R. We were looking at the same data set, this voting data set we've been looking at for some time now, and I'm just going to run all of this really quickly. But we did this exploratory data analysis. We looked at a basic simple linear regression and multiple linear regression model. We compared their training error and testing error. And so let me just load all this real quick. Cycling through some plots. Okay, so let's pick up. So so now we're going to look at some residual plots. Okay, so we've seen some of these in R already, but this is just how to produce them. So this is a plot of the residuals of that simple linear regression model where we're just predicting from percentage of search traffic related to NASCAR. So I'm plotting the residuals on a Y against the x-axis, which is NASCAR viewing. Okay, and so we see that problem with the residuals that I pointed out earlier, right? Here's the smoothing spline that I put in. Here's how to make a smoothing spline. So this just helps my eye keep track of the fact that indeed, yes, the mean is below 0 for low values of NASCAR, for communities that watch or that have a low percentage of their internet traffic related to NASCAR. Here's the y=0 line as a visual. The multiple linear regression residuals as 3 dimensions. Here's the plane to help my eye. So again, I'm looking for are these mean 0 constant variance for all values of NASCAR and NBA search traffic. Here I'm plotting this residuals of the multiple linear regression model against one of the predictors and against the other. So we've seen these plots in the slides. This is just how to make them in R. So this is against NASCAR, against NBA, and against the prediction y hat, right? And so then I'm just using this resid to extract the residuals, plotting against the predictors, and these are just some extra arguments for the plotting functions. To actually do the transformations, here's how I do it. So this is more residuals, but here I'm going to make a second degree polynomial, okay? And then in order to make this plot here, I'm plotting a prediction of this polynomial model on the x range defined by NASCAR. So I define this x range for NASCAR, and then I'm going to predict using this polynomial model, and that just allows me to trace out the curve here. So here's the x and y, and then if I plot these predicted points for this x range, I get this curve here. Okay. Again, we saw this in the lecture, but still, it's nice to see it how to do it in R. Okay. Same idea for so what are we doing here? Okay, so this is the residual of the multiple linear regression model defined using the polynomial predictors. Okay, so I made the model, put the curve through it. We're looking at the residuals, assessing the health of the assumptions, and again, just putting that line through it so I can assess my visualization. We still have problems with the quadratic model. Okay, smoothing spline again to help my eye, and a legend which will show up correctly if I make this window bigger. All right. This is the third degree polynomial model. The idea is the same. I'm just going to move through this one quickly. So what we do is we build a third polynomial model of order 3. We plot that curve, which predicts on the x range. Looks better. We can plot the residuals. Again, see that we appear to have reconciled the errors that we had over here. Stick a mean zero line through it to help my eye. And again, just proceeding quickly, the square root model, which we saw, the log model, which we saw, the log y against log x model, which we saw, just same game, different transformations. Okay. Plotting the squared residuals. The reason we do this is we're looking for constant mean here as a way to assess constant variance, right? Again, a smoothing spline. We've seen this smoothing spline before, but this is how we do it in R. I'm plotting the residuals against the predicted values. We can plot against any one of the predictors, but the predicted values is a way to is one way that we can plot against it. We can plot residuals in a multiple linear regression model. We can always just plot against the y hat value, since the y hat value is always univariate. Okay. This is the absolute residuals instead of the square residuals. Again, the idea being that it's easier to assess constant mean here when the scaling is not so blown up, as we see with the square of the residuals, and then the square root of the absolute value of the residuals, which, as we've discussed, is usually better on the eyes. It's easier to assess. Okay. A term plot. So here's the term plot. This is what I was talking about with the term plot. So what the term plot is doing is it's plotting the residuals. So this is what it's doing is it's saying, okay, the NBA term as a predictor, this is what it contributes to y hat, and you add the residuals to it. So what I'm looking for is, are we mean zero around this red line? Okay, and so when I do a term plot, I feed it a model. I do partial resid equals true. If I don't do partial resid equals true, it doesn't give me these gray points, and I'm not able to assess the residuals. So here's NBA. So NBA, NASCAR. Okay, again, sort of we have this residuals added to the part which contributes, the part of NASCAR which contributes to the prediction, and we can do that for our different models. So this is a way. What's nice about this is that it will bring up plots against the predictors quickly. So you don't have to do plot against NASCAR, plot against NBA. You can just do this term plot. But remember, you're not assessing mean zero. You're assessing sort of the mean should be around this red line. Okay, so if you were to subtract off this red line, you should see mean zero. Okay. We can compute the leverages by hand. Here I've built the H matrix, so the design matrix, and the hat matrix, x transpose x transpose, and then I'm plotting the residuals against the diagonal of the hat matrix, which defines the leverage. Okay, so here's a leverage plot. I'm selecting the high leverage cities. Those are the ones which have the diagonal terms greater than 0.1. And then I'm selecting which metropolitan areas are have this high leverage. Okay, so these are the cities that I showed on the slides. Again, plotting the high leverage points in red. And then lastly, we'll look at assessing normality as we did in the slides. This is plotting a QQ plot. I can do so with the QQ norm. So QQ norm applied to the residuals gives me this QQ plot, plotted against the normal distribution. Histogram of the residuals, I can assess normality there. Looks like it's reasonable that it could be normal distributed, right? It's bell-shaped. I can plot the kernel density estimation with plot density. And again, I'm looking for normality, and I don't see any evidence that it breaks. Therefore, it's reasonable for me to accept that assumption. Lastly, I mentioned you can plot the linear model. So this is when I plot the linear model itself. Again, this is the cubic model, my favorite one, the one that I thought satisfied the assumptions the best. Here is the residuals versus the fitted values. So this is the residuals on the y-axis, the y-hats on the x-axis. Here we're plotting them. We're looking for mean zero, constant variance, and we have this red smoothing spline to assist us. If I hit enter to see the next plot, I see the QQ plot where it's reasonable to me, again, that these residuals would be normal. So it's reasonable that the Gaussian error assumption could hold. Scale location, this is the plot where we plot against the root absolute value of the residuals. The root absolute values of the residuals. I said that right. This is plotted against y hat. So again, we're assessing constant mean here. And then the leverage plot, right? So this is a little more fancy than the leverage plot that I made because it includes Cook's distance information, but we still see, there's these 4 points, 4 or 5 points which have leverage bigger than 0.1, right? So it's the same plot. R will just do it automatically. So sometimes it's useful if you want to do something specialized, like be able to extract some information about, these high leverage cities. Being able to pull up this information by hand, the way that I've done it here, can be very important. But as a cursory analysis and a way to see a lot of information quickly, R's default plotting of the linear models is a very good tool, so I encourage you to use it. But understand what's going on under the hood. That's the reason we spend so much time on this, so we can dig in and do more detailed analysis than just the information that R presents us by default. Okay, so that's all I have to say for this lecture, and I will see everybody next time.